Hello, my name is Doug Doerfler, and today I will be describing our experiences porting the OpenCL version of SU3 Bench to FPGAs. Please also note my co-authors from Berkeley Lab and Polytechnique of Milan. In our evaluation, it is not the intent to directly compare the different devices, but instead to evaluate performance relative to the capabilities of the devices. Nominally, SU3 Bench is a memory bandwidth bound kernel, so in this case we evaluate the performance achieved relative to the maximum sustained performance of the respective memory subsystems. As a reference, studies exploring GPU architectures have demonstrated 75 to 90% efficiencies. We also investigated portability between the two vendor tool chains and source code changes necessary to move from the original GPU-based kernel design. What is SU3 Bench? It is a microbenchmark derived from lattice quantum chromodynamics codes, and the main kernel performs SU3 matrix multiplies, which is a dominant computational element in lattice QCD codes. In this study, we focus on the OpenCL implementation, but the microbenchmark has been ported to a wide variety of different programming languages. It is an open source code and is a member of the NERSC proxy application suite, which can be found at this URL. The master branch is primarily for GPU targets, but there is also a FPGA branch which was used for this study. The repository also contains all the necessary design files for both the Intel and Xilinx toolchains. I apologize for the source code iChart, but it does provide insight into the basics of the kernel. Inside a triple nested loop is a vector dot product using complex floating point operations. And for this study we looked at the single precision version. Each matrix is a fixed 3x3 dimension, and the calculation is carried out for each link in a 4-dimensional space. This is the nominal single work item kernel implementation, and the following analysis compares this to various variants in which the source code is not presented, but all source code can be found in the appendix of the paper. So I encourage readers to refer to the paper for details regarding the implementations. The kernel has an arithmetic intensity of 1.35 for the single precision version. This is a relatively low ratio of floating point operations per byte of data, and hence the kernel tends to be memory bandwidth bound for most architectures. The benchmark measures the time to enqueue the kernel, perform the specified set of iterations of the calculation, and return control to the host program. It does not include the time to move data over the PCIe bus. The size of the lattice is nominally 32 to the fourth for a total of over 1 million sites and a memory footprint of over 640 megabytes. For the Xilinx analysis, the size of the lattice was reduced to 16 to the fourth in order to fit into a single bank of high bandwidth memory. However, the size of the lattice for benchmarking only needs to be sufficiently larger than any local cache, and since the Xilinx device doesn't contain a cache, this was not an issue. In the following analysis, we will refer to NDRange and single work item versions of the kernel. NDRange is an OpenCL abstraction that partitions the work into multiple work items, which are operated on by an independent set of computational units. A single work item kernel is a single computation unit operating on the entire data set. In a NDRange kernel, the work item number is determined by an OpenCL API call, and if it's in a valid range, it operates on that work item. In the SWI kernel, there is an outside loop over all of the work items. In this study, we investigated two FPGAs and their respective OpenCL toolchains. The host test platform was common between the two and consisted of an Intel host processor connecting to the two FPGA cards over a PCIe bus. We investigated the Intel Arria 10 FPGA with the Quantus Prime version 17.1.1 development environment, and the Xilinx Alveo U280 with the Vitis Unified Software version 2019.2.1 development environment. Both devices contain two channels of DDR, and the Xilinx U280 also contains a high bandwidth memory subsystem. The best performance for the Intel toolchain was achieved with a single pragma and roll directive above the outermost loop. It should be noted that other Intel Quartus optimizations were explored, but not presented in detail in the paper, as they all demonstrated slightly worse performance compared to unrolling. Absolute performance is shown, but as mentioned previously, we normalized this performance to the maximum sustained bandwidth of the device. Another study has empirically determined that the Intel Arria 10 can achieve up to 25 gigabytes per second. With SU3 bench, we were able to achieve 15.8% and 47.6% of sustained bandwidth with the NDRange and SWI kernels respectively. It should be noted that the NDRange kernel is 3 times slower than the single work item kernel. The advantage of an NDRange kernel is the ability to define multiple compute units and hence to potentially increase the resource usage of the FPGA. But unfortunately, in this case, it actually slowed down the calculation. We also looked at the impact of interleaving of the DRAM channels. Disabling channel interleaving resulted in a 1.12 times speedup. However, this also requires a very large memory capacity footprint in order to span both channels, which may not be a very practical solution. Demonstrating the higher performance potential of the SWI kernel is not a major contribution of this paper, as it is a well-known issue within the community. However, in memory bandwidth bound situation, it is still interesting to understand what the upper bound is, taking into account the FPGA runtime overhead. In order to further explore the overhead, we composed an experiment in which the computational part of the kernel was removed, leaving only the loop level logic. The compilers may have even removed that logic, but it still must go through the OpenCL queues and be scheduled by the respective runtimes. In essence, this becomes a measurement of the overhead of the respective kernel types. Here we observe greater than a magnitude difference in performance between the two kernel types, but the overhead of the NDRange kernel is still sufficiently low such that it may not be the sole contributor to the low performance of our NDRange kernels. There may be reduced optimizations too. An inspection of the compiler report showed that the SWI kernel has implicit pipelining optimizations that the NDRange kernel lacked. Perhaps this is to reduce resource usage in anticipation of generating multiple compute units. For the Xilinx U280 analysis, we decided to focus on the HBM memory subsystem due to its higher performance. As a reminder, this is not a comparison of devices and their capabilities, but of a given device and the capabilities of its toolchain. Initially, we target just 2 of the 32 available HBM channels. It has been documented that there is a turnaround overhead associated with the U280 HBM memory controller when switching from a read to a write operation. So we dedicated 1 HBM channel for reads and 1 channel for writes. The intent was to expand to multiple channels once we better understand how to utilize 2 channels. Xilinx documents the maximum sustained bandwidth of a single channel to be 13.1 gigabytes per second. Due to the synchronous nature of our kernel design, that is, we read, then compute, then write the results, the maximum sustained bandwidth for our experiment is that of a single channel, 13.1 gigabytes per second. As with the Intel experiments, we attained the best performance with a SWI kernel. However, due to the lack of a cache implemented in the Xilinx FPGA, it is necessary to rewrite the kernel to include a local memory scratch pad, that is, local arrays, and to explicitly copy from global memory to the scratch pad. We don't show the source code here, but you can find it in the paper. Using a local scratch pad, we were able to obtain 35.3% of the maximum sustained bandwidth when using the SWI kernel. This is a performance increase of 27 times the version without the scratch pad. The advantage of the scratch pad version is primarily in the data movement operations. With the scratchpad logic, the compiler is able to schedule 512-bit burst transfers. Without the scratchpad, it only schedules 64-bit transfers. This and more effective burst transfers enable more effective use of the HBM interface. In this scratchpad version, data is copied from local memory in a specified chunk size, then the calculation is performed on the scratchpad, and then the results are written back to global memory. This results in the same triple nested loop being called 3 times for each burst into local memory. From a programmer's perspective, this seems highly redundant. What if we combine the transfer from global to local memory within the calculation? This is a more intuitive code structure and how a programmer would want to write it initially. However, when doing it this way, the compiler no longer schedules burst transfers and performance drops by a factor of 3.8. It's critical to understand what the compiler wants in order to write high-performance code using the Xilinx toolchain. In summary, we include some of the portability considerations we discovered in our study. The first is that even though it is well understood that a SWI kernel performs best when targeting a FPGA, this is not the preferred method for writing parallel OpenCL programs. It is desirable that the vendors improve the performance of the NDRange runtime to ease the transition of kernels written for CPUs and GPUs, and to ease the programmer's burden when multiple compute units can fit on a single device. Using block RAM as a cache greatly simplifies the programmer's extra effort. The Intel toolchain can synthesize a cache using block RAM automatically, and this made the path to high performance on the Intel device pretty straightforward. However, with the Xilinx toolchain, one must explicitly copy data to a local memory scratchpad, and it must expose those data structures properly to ensure it schedules 512-bit burst transfers. This requires intimate knowledge of how to write code that presents itself to the compiler in a way that ensures it recognizes a burst transfer. One can read the compiler reports to determine when it does, but even this takes some level of expert knowledge to interpret the compiler reports. The Xilinx toolchain requires explicit pipeline directives and implicitly unrolls loops. The Intel toolchain is just the opposite. This alone makes it nearly impossible to write a single source code that can be ported between the two without modification. In addition to the portability of the kernel code, it was also necessary to make host-side source code changes for the Xilinx toolchain. Please read the paper for more details, but in particular, when writing C++ code, it is necessary to use a custom standard vector library allocator to ensure 4096 byte alignment in order to ensure optimal PCIe transfers and to avoid those pesky warning messages. In conclusion, we did find that from a functional perspective, both toolchains were relatively easy to use and obtain initial results, disregarding the expected long compile times when fully synthesizing the logic. We were able to achieve 35 to 48% architectural efficiencies on the FPGAs. In comparison, our studies on GPUs have shown 75 to 90% efficiencies. Although it is well known that SWI kernels perform better, this is not how OpenCL code is written for CPUs and GPUs. It is highly desirable that vendors improve their NDRange implementations to ease the transition of existing codes. This also makes it much easier to scale the design to multiple compute units without adding extra host-side code to manage multiple queues for multiple SWI kernels. We encountered quite a few issues with the Xilinx toolchain to ensure efficient 512-bit burst transfers. The Xilinx HLS compiler provides a more robust programming environment for its FPGAs. Perhaps we should have used this instead, but that would have made OpenCL portability a major concern. But using HLS may have eliminated many of the issues we have encountered. Thank you for your time and interest in our study. You can find more detail and complete kernel source code listings in our paper at the following URL.